So May, who has a mass of 79 kilograms, and Amber, who has a mass of 51 kilograms, stand motionless on skates. What does that mean? Motionless on skates, on ice skates. Well, on ice skates, it implies that there's no friction, right? So whenever they say ice and all that stuff, so we ignore friction. Okay, and stand motionless means that they're at rest or their initial velocities are 0 meters per second, right? Facing each other at arm's length on a smooth frozen pond. Again, the frozen pond thing means that there's no friction. Which of the following actions will give Amber the least amount of speed? So then it gives you a list of different choices, but let's just draw the picture real quick. So I have May here. Somebody made fun of me because I drew Jordans on myself. They said I took, how did they word it? Painstaking, meticulous. I don't remember what they said, but they said that I was I spent a lot of time drawing a picture of myself with Air Jordans. I just thought it was funny. So, anyways, they're actually closer to each other than this. So, let's do it this way. Oh boy, never mind. We'll just leave it like that. Let's just assume they're right next to each other. Which one would give the least speed? So this is more of an impulse situation. So remember that J is the letter for impulse because we use I for a bunch of other stuff. And that J is equal to the change in momentum, right? And the change in momentum, really their masses don't change, but their velocities will. Because there's, in other words, their initial velocity, both of these people, this, we'll say that this is the initial velocity of May, which is 0 meters per second. And then Amber's initial velocity is equal to 0, and we'll put an A here for Amber. And they're going to push against each other, and, or, you know, we're not quite sure, but they're at arm's length away. Which one will give them, will give Amber the least speed? Now, momentum is based on their mass, and as you can see, May has a greater mass than Amber. Now, what that means is May is less likely to move, or she won't move as much. Well, let me rephrase that. Remember that momentum P is equal to the mass times the velocity. So because May is more massive, her velocity will be lower, right? Her momentum would be, well, it has to be conserved, right? So if I add up their initial momentum, their total initial momentum in the beginning, the initial, I totally misspelled the word momentum. And I am kind of over explaining this, but that's okay. I think it'll help you guys in the long run. So the initial total momentum is May, which is 0, right? Doesn't matter what her mass is. 0 times 79 is 0, plus Amber, which is 51 times 0, right? Because we're saying the mass times their velocity, but their velocity is 0, So that means that May's final velocity, if she moves at all, is going to go this way, which is in the negative direction, right? And then Amber's final velocity is going to go in this direction, which is a positive and a negative. But remember, the momentum is conserved, so their final momentum because it's conserved, also has to equal 0. And I'll just stop there, equals 0. Okay? All right, so then one last thing. So remember that force, if I write out the change in velocity, m, the change in velocity is actually the final velocity minus the initial velocity, right? That's the change in momentum. Over, well, let me back up. That's the change in momentum. So if we do a little bit of algebra, we also get that our change in momentum is equal to the force times time. Now where that comes from is if I divide this by time but multiply by time, remember if I multiply the top and bottom by the same thing, they cancel out. So this t cancels out with this t, but this t, and we could think of it as delta t, and this would also be delta t. This is actually acceleration. So the force, right, the force comes from the fact that if I take this, which is mass, times this stuff, which is really acceleration, well, force is mass times acceleration times delta t. That's where all that comes from. It's a little algebraic manipulation. So then the final answer boils down to, since Amber is motionless in the beginning, her final velocity, if we wanted to find her final velocity, would basically be her momentum divided by her mass, right? So if we did a little bit more algebra, her final velocity, in other words, let me show you what I mean by that. We're basically saying that the mass of Amber times the change in velocity, which is actually the final velocity minus the initial velocity, is also equal to the force applied times the time that that force is applied. While her initial velocity is 0, so we get that the mass of Amber is equal to the force times time. Oh wait, let me back up. We gotta multiply this. So let me get rid of this. So I'm going to multiply this times this, so we get that the mass of Amber times the final velocity equals this. And so we're really trying to determine the final velocity. Now we don't have enough numbers and we don't have to do the math, but I just want you to think about this conceptually. So her final velocity can be calculated by the force times the time all over her mass. So then if we go back and look at that question, they basically give us a number of options. Okay? And so the correct option in this particular case is this one, which is C. Amber pushes with a force of 300 newtons for 0.4 seconds. And because May is more massive, she won't move as much. So then, basically you would have to do the math, right? So this would be your force is the 300 newtons, and the time will be 0.04. Now, some people, and so you'd have to go through all the options, and so it has to be Amber pushing in this particular case because May is more massive. So that it's almost like if I push against this wall is so massive because it's attached to the building, so I'm really pushing against the weight of the building. I can't move the wall, so I move backwards. It's the same thing with May and Amber. Now May will move a little bit, but the thing that has the most impact on Amber is Amber pushing. Now, if Amber was more massive, then it might be different. But this problem's kind of rigged up to where you have to do it this way. And so you would actually find the one, since they want to know which one is the least, which would give her the least speed, you'd have to go through and multiply all the forces Amber has to push. I think the other option was this one. This was the other option, which was, oops, let me undo that. The other Amber pushing option was this one. And this one isn't as effective because if you do the math on that, if you multiply 400 times 0.08, that's bigger, right? So if I take this number and then I multiply that by this number, that's going to give you a bigger velocity. Does that make sense? So if this question was on the test, and I said, and I changed it, and I said, what is the greatest velocity? You still have the same setup that you have here, but then you would have to multiply this out and multiply this one out and see which one was greater. That's why I went through and explained this whole thing. Okay, does that make sense? All right. Sometimes you have to do that, and now you could actually, you could plug in. Remember that her mass that was given to us was what, 51? So it's still the force. The thing that has the greatest impact is this stuff right here. Does anybody have any questions on that? Does that make sense? Thumbs up if that makes sense. Thumbs down if you're like, it's too early in the morning.